Hey there, deep divers. Ready for another deep dive? Today, we're going super small to the heart of matter, the atom.
Smaller than small.
And we're going to explore something called isotopes.
Yeah.
I think most of our listeners have probably heard of atoms and, the basics like protons, neutrons, and electrons, right?
Right.
Well, isotopes are like, how do I put it? Different flavors of the same element, but with a twist.
Yeah, that's one way to think about it. Like, imagine if you had a set of building blocks, right?
Hmm.
And each element is represented by a different color block. So, like, blue blocks for carbon, red blocks for oxygen. You get the idea.
Okay, I'm visualizing it. So where do isotopes fit into this block analogy?
Well, isotopes would be blocks of the same color, but with slightly different weights.
Oh, I see. So it's like having a set of blue blocks for carbon, but some of those blue blocks are a bit heavier than others.
Exactly,
Yeah.
because they have a different number of neutrons.
Right, neutrons, those neutral particles hanging out in the nucleus.
Hmm.
So more neutrons equal more weight.
Precisely. They still have the same number of protons, which determines what element they are, but that neutron count can vary, giving us different isotopes of the same element.
Okay, that makes sense. But why does this tiny difference in neutron count matter so much? It's just a couple of extra neutrons, right?
Well, those extra neutrons can actually tell us a lot about the world around us. For one thing, they affect an atom's stability.
Stability. You
Like,
mean like how likely it is to stay the same element and not transform into something else?
yeah, exactly. You see, those protons and neutrons in the nucleus, they're held together by a very powerful force called the strong nuclear force. And the strength of that force, what we call the binding energy, depends on the number of protons and neutrons.
Okay, so it's like the glue holding the nucleus together.
Mm-hmm.
And different isotopes have different glue strengths.
That's a great analogy. Now, here's where it gets really interesting. The binding energy per nucleon and a nucleon is just a fancy term for either a proton or a neutron well. That binding energy per nucleon isn't the same for all elements.
Meaning some elements have stronger glue than others.
Precisely. And it turns out that iron, with 26 protons and usually around 30 neutrons, has one of the highest binding energies per nucleon.
So iron is like the champion of stability in the atomic world, holding its nucleus together with super strong glue.
You could say that.
That-
And this difference in binding energies, well, it also explains why some isotopes are more common than others.
Oh, how so?
Well, isotopes with even numbers of protons and neutrons, they tend to have higher binding energies and are therefore more stable. And what's more stable is usually more abundant in nature.
Ah, so it's like a cosmic balancing act.
Yeah.
More stability equals more abundance. Makes sense.
Hmm.
But what about those isotopes that aren't so stable? What happens to them?
While some isotopes are, shall we say, a bit more energetic, they're what we call radioactive.
Yeah, radioactive. Like uranium. I remember learning about that. It's constantly breaking down and releasing energy.
Exactly. And it's not just uranium. There are lots of radioactive isotopes out there. They undergo a process called radioactive decay, where they kind of transform into a different element over time.
It's like they're slowly changing their identity, like a radioactive chameleon.
I like that. And there are actually different types of radioactive decay, each with its own unique characteristics. For example, there's alpha decay, where a heavy nucleus basically spits out a particle consisting of two protons and two neutrons.
Wait, so it's like spitting out a tiny helium nucleus. Helium has two protons and two neutrons, right?
Precisely. And by losing those two protons, the original element actually changes into a different element. Then there's beta decay. That's where a neutron in the nucleus decides it wants to become a proton. And in the process, it releases an electron.
So that's another way an element can change into a different one by changing the number of protons. Pretty neat. What other kinds of decay are there?
Well, there's also gamma decay. In this case, the nucleus releases energy in the form of gamma rays, but it doesn't actually change its composition. It's more like releasing some excess energy to become more stable.
Okay, so it's like the nucleus is letting off some steam. So we've got alpha, beta, and gamma decay. It's amazing how these tiny events at the subatomic level can have such significant effects.
Absolutely. And these processes aren't just theoretical, they have real-world applications. Radioactive isotopes are used in medicine, industry, you name it.
Oh, right. Like I remember learning about carbon dating. They use carbon-14, which is a radioactive isotope of carbon, to figure out how old things are, like fossils and ancient artifacts.
Exactly. And in medicine, radioactive isotopes are used in imaging techniques like PET scans and for treating certain types of cancers. It's amazing how scientists have figured out how to harness these atomic processes to solve real-world problems.
It's like we've unlocked the secrets of the atom and put them to work. But, I've always wondered, do all elements have a fixed and unchanging isotopic composition? Like, is the ratio of isotopes always the same for a given element?
Well, it's not quite that simple. While most elements do have a generally consistent isotopic composition across the Earth, there are certain things that can cause variations.
Oh, really? Like what? Spill the beans.
For one, there's something called radiogenic nuclides. These are nuclides formed by the decay of radioactive parent isotopes.
Okay, so it's like a chain reaction where one radioactive isotope decays into another.
Exactly. And as that parent isotope decays, it continuously produces the radiogenic daughter nuclide. And this can gradually change the overall isotopic composition of the element over time.
So it's like a constant game of atomic transformation happening within these elements.
Precisely. Take strontium, for example. It has a stable isotope, strontium-87, that's produced by the radioactive decay of rubidium-87. By measuring the ratio of strontium-87 to other strontium isotopes in a sample, we can determine the age of rocks and even trace the origins of different geological materials.
So these isotopes are like tiny time capsules, holding information about the history of our planet.
That's a great way to put it. And lead is another great example. It has several radiogenic isotopes, lead-206, 207, and 208, formed by the decay of uranium and thorium isotopes. This makes lead isotopic analysis super useful for dating rocks and minerals and even tracing sources of lead contamination in the environment.
So radiogenic nuclides can definitely shake things up in terms of isotopic composition. What else can cause these variations?
Well, sometimes it's not from Earth at all. Extraterrestrial materials like meteorites can have isotopic compositions that are totally different from those found on Earth.
Oh, that's right, because they formed in different parts of the solar system, right? They were exposed to different conditions and processes.
Exactly. So by analyzing the isotopes in meteorites, we can actually learn about conditions in other parts of our solar system billions of years ago. It's pretty amazing, isn't it?
It's mind-blowing. It's like holding a piece of the early solar system in your hand and decoding its secrets.
And there's even more. Did you know that even interactions between cosmic rays and terrestrial matter can cause isotopic variations?
Wait, those cosmic rays again? I thought we were done with them.
They're everywhere. Remember, those high-energy particles are constantly bombarding Earth from space. And when they collide with atoms in the atmosphere or on the surface, they can trigger nuclear reactions that produce new isotopes.
So it's like the universe is constantly showering us with these tiny atomic messengers, each carrying a unique story.
That's a beautiful way to think about it. And one of the best-known examples of this is the production of carbon-14, which we talked about earlier, from nitrogen-14 in the atmosphere. This is actually the process that makes radiocarbon dating possible.
So even though carbon-14 is radioactive and decays over time, it's constantly being replenished by those cosmic rays. It's like a never-ending cycle, creating this equilibrium that allows us to date ancient materials. Nature is pretty incredible.
Absolutely. And it gets even more interesting when we start talking about mass-dependent isotope fractionation. This is where the subtle mass differences between isotopes actually come into play during physical processes and chemical reactions.
Okay, mass-dependent isotope fractionation. That sounds a bit complicated. Break it down for us.
Basically, it means that heavier isotopes tend to be a bit more sluggish than their lighter counterparts.
Sluggish, like they move slower.
Yeah, in a way. It leads to tiny variations in their distribution. Imagine a process like evaporation. Lighter water molecules containing the lighter oxygen-16 isotope, they'll evaporate slightly faster than heavier water molecules containing oxygen-18.
Interesting. So the lighter isotopes have a slight advantage in the evaporation race. Does this happen with other elements too?
Absolutely. It can happen with any element that has isotopes. And this phenomenon can be used to understand a wide range of processes, like the formation of minerals or the movement of pollutants in the environment.
Okay, I'm starting to see how these tiny variations in isotopic composition can actually help us understand some pretty big processes on Earth.
Exactly. And we're just scratching the surface here. There are even more complex processes like mass-independent fractionation, where certain isotopes just don't follow those neat mass-based expectations.
Oh, that sounds like a whole other deep dive.
It is, and we're going to explore that fascinating realm in the next part of our journey. Stay tuned.
Okay, so mass-independent fractionation, huh? It's like the rebel of the isotope world, right? Breaking all the rules we just talked about.
You could say that. It's definitely the more mysterious side of isotope behavior. You see, with mass-dependent fractionation, it all makes sense, right? The heavier isotopes are a bit slower, so we see these predictable patterns based on their mass difference. But with mass-independent fractionation, things get a little, well, weird.
Weird how? Give me an example.
We see these variations in isotopic composition that just don't fit those nice, neat expectations based on mass. It's like some isotopes have a mind of their own.
So what's going on? Why do some isotopes decide to go rogue?
Well, it's still a bit of a puzzle, and scientists are working hard to figure it all out, but there are a few really interesting theories out there. One of them has to do with the nuclear volume effect.
Nuclear volume, you mean the size of the nucleus?
Exactly. You see, even though isotopes of the same element have the same number of protons, their nuclei can actually have slightly different sizes and shapes.
Wait, hold on. The nucleus has a shape. I always thought of it as just this tiny point at the center of the atom.
Yeah, that's a common misconception. The nucleus is incredibly small, that's true, but it's more than just a point. It's a dynamic structure made up of protons and neutrons, and the arrangement of those particles can lead to subtle variations in nuclear size and shape, especially for isotopes with odd numbers of neutrons.
So it's like even the nucleus has its own unique personality.
You could say that. And these tiny variations in nuclear volume, well, they can actually influence how isotopes interact with the surrounding electrons during chemical reactions.
Okay, I'm trying to picture this. So it's like a tiny dance between the nucleus and the electrons, and the steps change depending on the isotope's nuclear volume.
Exactly. And this slightly altered dance, well, it can lead to mass-independent fractionation, where isotopes don't behave exactly as we'd predict based on their mass alone.
Okay, that makes sense. But the source material also mentions something about the magnetic character of some nuclei playing a role. How does that fit into all of this?
Ah, yes. Now we're getting into some really cool stuff. Some isotopes, particularly those with an odd number of protons or neutrons, have this property called nuclear spin. It's like they have a tiny internal magnet.
So they're like tiny spinning magnets.
A great way to visualize it. And because they have this nuclear spin, they interact differently with magnetic fields, including the magnetic fields generated by the electrons in their own atom.
So their magnetic personalities can influence how they bond with other atoms.
Precisely. This interaction can subtly affect the rates of chemical reactions, and that can lead to mass-independent fractionation. There's a classic example with the methylation of inorganic tin, using methylcobalamin. Typically, this reaction shows normal mass-dependent fractionation. But if you expose it to UV radiation, suddenly those odd-numbered tin isotopes, the ones with nuclear spin, show a much larger fractionation effect.
It's like the UV light flips the switch, activating their magnetic superpowers. So this mass-independent fractionation is pretty fascinating, but is it just a scientific curiosity, or does it have any practical applications?
Oh, it's definitely more than just a curiosity. Mass-independent fractionation gives us this unique fingerprint, you could say, that helps us identify the sources of elements in the environment.
Okay, I'm intrigued. How does that work?
Let's take mercury, for instance. It's a toxic element that can build up in organisms, and it poses a risk to human health. But by analyzing the mass-independent fractionation patterns of mercury isotopes, well, we can trace mercury pollution back to its source, like whether it's from industrial emissions or volcanic activity or maybe even natural geological processes.
It's like an isotopic detective story, using these tiny variations to track down the culprits.
Exactly. And this approach isn't limited to mercury either. Scientists are using mass-independent fractionation to understand the cycling of all sorts of elements: chromium, tin, even uranium.
It's amazing how these tiny atomic variations can give us such big clues about what's happening in the environment.
It really is. And speaking of shaking things up, did you know that even humans can mess with the natural isotopic composition of elements?
Oh, right. Like with uranium enrichment for nuclear power and weapons, right?
You got it. To make nuclear fuel or weapons, you need to increase the concentration of the uranium-235 isotope. And they do that using centrifuges. They spin uranium hexafluoride gas at super high speeds. And since uranium-235 is a bit lighter than uranium-238, they can separate them.
Yeah, it's a pretty intense process.
Yep.
And it definitely has huge implications, both good and bad.
That's right. Enriched uranium can be used for good, like generating electricity, but it can also be used to create nuclear weapons. It's a reminder that scientific discoveries can have a double-edged sword.
It definitely makes you think.
Yeah.
And is uranium the only element where humans are messing with the isotopic balance?
Not at all. We see it with lithium too. Lithium-6, it's used in thermonuclear weapons, and because of that, it's actually depleted in some chemical reagents, kind of a side effect of weapons development.
So even in seemingly mundane things like chemical reagents, we can find traces of human activities and their impact on the atomic world.
It really highlights the interconnectedness of science and society, doesn't it? how even the smallest atom can have far-reaching consequences. Now, the source material also mentions boron, that element found in laundry detergent and insecticides. It turns out to be quite the interesting character in the world of isotopes.
Okay, I'm curious, what's so special about boron?
Well, boron has two main isotopes, boron-10 and boron-11. And they have very different properties when it comes to interacting with neutrons. Boron-10, it's like a neutron-absorbing superstar.
What do you mean?
It has this incredibly high probability of capturing neutrons. It's like a neutron magnet.
So does this have any practical uses?
Absolutely. This property makes boron-10 incredibly useful in controlling nuclear chain reactions. That's why boron-10 enriched boron is used in control rods in nuclear reactors. It helps regulate the rate of fission, make sure things don't get too hot, so to speak.
So it's like the brakes on a nuclear reactor?
A perfect analogy. And boron-10 is also a key player in a really promising cancer treatment called boron neutron capture therapy. They deliver boron-10 to tumor cells and then zap the area with neutrons. And that boron-10, it captures those neutrons, releases alpha particles that destroy the cancerous cells.
Wow, that's amazing. It's like boron-10 is a double agent in the fight against cancer.
Right. It really highlights the power of understanding and manipulating isotopes, doesn't it? I mean, there's so much potential there, from advancing medicine to addressing environmental challenges and even harnessing the power of the atom.
Well, that was an amazing journey through the world of mass-independent fractionation. From nuclear spin to human intervention and even cancer-fighting boron, it's clear that isotopes hold many secrets. But wait, there's still more to this story, right?
Of course. Remember those cosmic rays we talked about? They're not just creating carbon-14, they're constantly bombarding Earth, producing a whole shower of cosmogenic nuclides.
Cosmogenic nuclides, they sound like something straight out of a comic book.
And they're just as amazing. These isotopes can tell us even more about our planet's history.
Okay, I am hooked. Cosmogenic nuclides, it is. Let's dive into that in the next part of our deep dive. Okay, cosmogenic nuclides. They sound like something straight out of a sci-fi movie.
They might sound like science fiction, but they're very real. And they can tell us some pretty amazing things about our planet. Remember those cosmic rays we've been talking about? Those high-energy particles from space?
Yeah, the ones that are constantly bombarding Earth.
Exactly. Well, when those cosmic rays collide with atoms in the atmosphere or on the Earth's surface, they can create new isotopes, and we call those cosmogenic nuclides.
So it's like cosmic rays are these tiny atomic alchemists transforming elements into new forms.
I like that analogy. And these cosmogenic nuclides, they're like tiny time capsules, holding information about Earth's history. The processes that have shaped our planet over millions of years.
Okay, now I'm really intrigued. What kind of information can these cosmogenic nuclides reveal?
Well, one really cool application is in something called surface exposure dating. Imagine you have a rock surface that's been exposed to the elements for a very long time, maybe thousands or even millions of years.
Okay, I'm picturing a rocky mountaintop exposed to the wind and rain.
Perfect. Now, as those cosmic rays constantly bombard that surface, they produce cosmogenic nuclides, like beryllium-10 and aluminum-26.
So the longer a rock surface is exposed, the more of these cosmogenic nuclides it accumulates.
Exactly. And by measuring the concentration of those isotopes in the rock, scientists can actually determine how long that surface has been exposed.
It's like a cosmic clock ticking away on the surface of rocks, recording Earth's history.
A perfect analogy.
Yeah.
And this technique has been used to date all sorts of geological features like glacial moraines, fault scarps, you name it. It helps us understand things like rates of erosion, the frequency of earthquakes, and even the long-term effects of climate change.
It's amazing how something as seemingly abstract as cosmic rays can provide such concrete information about Earth's past.
It really is, and it goes beyond just dating surfaces. Cosmogenic nuclides can also be used to track the movement of glaciers. You see, as glaciers flow, they scrape and erode the underlying bedrock, exposing fresh surfaces to those cosmic ray alchemists.
So as glaciers move, they're creating these new canvases for cosmogenic nuclides to form.
Exactly. And by analyzing the distribution of cosmogenic nuclides in glacial valleys, scientists can reconstruct the past extent and movement of ice sheets, giving us clues about how climate change has shaped our planet over time.
Wow, it's like these isotopes are leaving breadcrumbs, allowing us to trace the footsteps of ancient glaciers. But there's one thing I've always been curious about. Earth's magnetic field, the one that protects us from solar radiation. Does that have anything to do with cosmogenic nuclides?
It actually does. You see, Earth's magnetic field acts as a shield, deflecting those harmful charged particles from the sun. But this field isn't static. It fluctuates in strength and can even reverse polarity over time.
Wait, reverses polarity? You mean the north and south magnetic poles can flip?
It might sound strange, but it's true. And these magnetic flips, they actually leave a record in the form of cosmogenic nuclides.
Okay, I'm not sure I follow. How do cosmogenic nuclides record magnetic flips?
Well, the production of cosmogenic nuclides is influenced by the strength of Earth's magnetic field. So, by analyzing the concentration of these isotopes in things like sediments and ice cores, which act like historical records, scientists can actually reconstruct the history of these magnetic flips.
So it's like these cosmogenic nuclides are like tiny magnetic compasses frozen in time, recording the ancient whispers of Earth's magnetic field.
I love that imagery. And this information is so valuable for understanding the complex dynamics of our planet's core and the long-term behavior of Earth's magnetic field, which, as you said, plays a crucial role in protecting life on our planet.
Wow, what an incredible journey this has been. From the basics of atomic structure to the mysteries of mass-independent fractionation and the secrets revealed by cosmogenic nuclides, it's clear that isotopes are more than just tiny particles. They hold the keys to understanding so much about our universe.
I completely agree. We've seen how isotopes can unlock secrets about the age of our planet, the origins of meteorites, the processes happening inside stars, and even the history of Earth's magnetic field.
It's truly remarkable how something so small can tell us so much about the vast universe we live in. And, I have a feeling we've only just scratched the surface. There's still so much more to discover in the realm of isotopes.
Without a doubt, the field is constantly evolving, and with each new discovery, we gain a deeper understanding of our world and our place in the cosmos.
Well said. So, to all our deep divers out there, keep exploring, keep questioning, and never stop being amazed by the wonders of science.